We're we're recording. We're recording now. So all right. Remember, make me look good. Let's practice it. 1, 2, 3. Ha ha ha. All right. There we go. Well done. Well done. You guys are making me look good. I appreciate it. Thank you. All right. So we're going to work on section 9.4. And let me start out with an example like this where we're multiplying radicals. And I hope this helps out with some of the other sections too. So I'm going to try and keep it a little bit more general. And I'm also going to color coordinate things a little bit for us. So the thing is, when you're multiplying radicals like this, the stuff on the outside multiplies. So negative 2 times 3 gives me negative 6. And then the stuff under the radical, which would be this, that multiplies. So 3 times 18 is 54. Okay? But unfortunately, we're not done here. There's a little bit more work we have to do. So let's work on splitting up 54. Can anyone think of a perfect square that evenly divides 54? What number is on that left-hand side board? 9 and 6. Perfect. Thanks, Patrick. So 9 and 6. So that's nice. What's the square root of 9? 3 times negative 6 is negative 18. So there you go. Negative 18 times the square root of 6. That's the final answer that I'll be looking for. Let's try a couple more. They're going to get harder. Oh, I know. The crowd goes wild. All right. Yeah, better. Much better. Thank you. Okay. Negative 2 times the square root of 7z cubed times 3 times the square root of 14z to the 8th. And again, you've got things outside and things inside. So let's start out with the stuff that's outside, which is, again, a negative 2 and a negative 3. So kind of cursing myself for a lack of variety on that one. Bad news. So negative 6 here, but that's a positive 3. Did I say negative 3? All right, my bad. I'll go back and look at the tape later. Okay. Now, underneath the radical, you've got a 7 and a 14. So let's put that underneath the radical. 7 times 14 is 98. And then there's one other thing that's underneath the radical here. That's the z's. Z to the third times z to the 8th. What happens when you multiply things with the same base? Add the exponents. So z to the 11th here. And all these things are color-coded, so I hope you can follow along there. But like the last one, we're not done. We need to split this up into a couple radicals. So negative 6 times something else. Good. So you're looking for a perfect square that goes into 98 evenly, and that would be 49. 49. And then a 2 here. Now, as far as the variables are concerned, that's a little bit different of a story. Even though it's not written, what index is understood to be out here? 2. So this is going to simplify pretty nicely as long as this number is evenly divisible by this index. And 11 is not nice and easily divisible by 2. But what number close to 11 is evenly divisible by 2? 10. So I'll take 10 of them and put them here. How many does that leave behind? 1. So this is my perfect square, and this is just kind of like the leftovers. Okay with that? All right. Well, all right. So square root of 49 is 7. How about the square root of z to the 10th? Yes, z to the 5th. Take this number and divide it by the index. Now, it's not written again, but it's understood that there's a 2 out there. 10 divided by 2 gives me z to the 5th. There. All right. The last part just kind of stays here. That's the square root of 2z. I'm going to clean this up just a little bit. So negative 42 z to the 5th square root of 2z. How are we looking on that one? All right. Good question. Where did the 42 come from? There you go. You answered your own question. So the negative 6 times 7 gives me the 42 there. All right. Hopefully not as bad as you were fearing. We'll do a couple more like that. Any thoughts on this? Something maybe I went over a little too fast? Chantel?
Just to clarify, no, you're good. So at the z to 11, if that was, for example, z to the 5th, then this negative 6, 49z would be, if I said that would be.
If this was a z to the 5th, then again you'd want to put something. Yeah, you'd put a 4 here and a 1 there. Yeah. So okay, good. There was another question. This one here. Okay. So the square root of 49 is a 7, and then with the exponents, when you have a variable to some power and you're trying to take its root, this gets divided by this. So 10 divided by 2 gave me the z to the 5th. So what worked out nice about this is that this was even, and it was evenly divisible by that 2 out in front. Now later on, we're going to do some that have, in fact, in the next problem, we'll do one that has a 3 out here. So that means instead of a multiple of 2 here, I'm going to want a multiple of 3. But it's the same idea. You want this power to be evenly divisible by this one. And that'll make it a root that simplifies very nicely. And then the rest is just 6. Okay, good. All right, sure. So, negative 6 times the cube root, and that's a cube root, sorry if it doesn't look that way, of 20a cubed, or it'll do a squared, and negative 2 times the cube root of 16a cubed. So, okay. Same kind of thing as the last one. We'll start out by multiplying the stuff that's on the outside of the radicals. So that's negative 6 times negative 2. That gives me a positive 12. And then I'll have a cube root of a couple things. And the first one would be 20 times 16. 20 times 16 is 320. And a to the second times a to the third would be a to what power? A to the 5th. So there, a to the 5th. Now, kind of like the last one, I want to break this up into a couple different radicals of a 12 and the cube root of something times the cube root of something else. Now this time, instead of looking at my list of perfect squares, what list am I going to look at? Cubes. So 1 cubed is 1, 2 cubed is 8, 27, 64, 125, 216, 343, etc. I think that's high enough. So 320 fits in here. Work your way up that list. Find the largest perfect cube that evenly divides that number. Somebody said it. 64 goes in there 5 times. 64 and 5. Now, Lisa, this was the part that you were kind of curious about in the last one. When we were dealing with square roots, I wanted a number here that was close to 11, but evenly divisible by 2. And that turned out to be 10. This time I'm dealing with cube roots. So I want something that's evenly divisible by 3 and close to 5. 6 would work, except we don't have 6 of them here. That's more than we got. So we can't do more. You got to do less. So if you're doing less, what's our only choice? 3. Now if I have 3 of them here, that leaves 2 of them here. Good with that one? Let's simplify the root then. That's going to be 12 times what? Cube root of 64 is 4. Cube root of a cubed is a. And then this is just the leftover, so nothing's going to happen there. 5a squared. I would appreciate if you multiply 12 times 4 for me. I'll do that for you just this once. All right, so that's a spot where you could laugh, but that's okay. Yeah, all right. That was weak. All right, are we okay with this one? All right, good, good. Your turn for 1. And it's going to look like this. Negative 5 times the cube root of 9r to the 8th times 7 times the cube root of 12r to the 7th. And I'll put this up here as well. So that's your list of perfect cubes. And I'll also put something else up. So, interestingly enough, I don't really have a pause button on this software. Yeah. So I'm putting the manual pause. There we go. Okay, so let's look at this one. First things first, the stuff on the outside multiplies together, so negative 5 times 7 gives me negative 35. So let's get that up there. Negative 35. And then the cube root, well, let's see. Trying to keep consistent here. So 9 times 12 is 108. 108. R to what power? R to the 15th. So R to the 15th. Now we're going to break this one up. This is going to be negative 35 times the cube root of something times the cube root of whatever's left over. Yes, well done. So you're looking for a number. You start out here. That's where your 108 is, and you work your way up the list. 64 doesn't go into 108 evenly, but 27 does. So we'll put a 27 here. R to what power? 15. Yeah, you can use all of them, right? Because 15 is evenly divisible by 3, so we're good. So that's in this first one, and all you're left with is cube root of 4. So it's negative 35. Cube root of this is going to be 3 r to what power? R to the 5th times the cube root of 4. Please don't lose the cube in part of that. So that's negative 105 r to the 5th times the cube root of 4. Whew. All right. Well done. Well done. How many people got that one right? Till the end? Yeah, please. Right. Right. Yeah, if it goes up. So why did we get lucky in this one? Is because 15 was already divisible by 3. So that's why we got lucky. In the previous ones, previous one, 5 wasn't divisible by 3, so you had to play around. Or in the one up here, 11 wasn't divisible by 2, so again, you had to play around a little bit. So had this been z to the 12th here, we would have been in good shape. All right. So anything else on this one? That was a good one. If you got that one right, give yourself a nice little attaboy, attagirl, because that was a tough one. So, all right. And for the benefit of my visual, my audience, there's a few people slapping themselves on the back. Okay, good job. Let's try some more here. And for this, I'm going to go to right out of Newton itself, just to make sure that we're doing problems like you're going to get in Newton. And we're going to start with this one, the square root of 9. There's 9 minus the square root of 5, quantity squared. So let me switch back to live action over here. And it's going to be 9 minus square root of 5 squared. Please, in doing these, do not just go, oh, that's going to be 81 minus 5, or 81 plus 5. Yeah. That would definitely earn you a frowny face at the very least. All right. What do I have to do to figure this one out? Foil it. Good. And that's going to mean for us multiplying the binomial by itself. So let's do that. We'll start with the first terms. So that's these. So 9 times 9 is 81. And then the second part, outside terms. Now what's the 9 going to multiply by when I multiply the outside terms? Yeah, basically by the negative, right? It's 9 times negative 1. Because this 9 is not under a radical. It's outside a radical. So the only thing it's going to multiply is the negative here. I'll get negative 9 times the square root of 5. And then let's keep going with the inside terms. So the inside terms would be these. What's the product of the inside terms going to give me? Negative 9 square root of 5. Again, you shouldn't be surprised to see that term twice. That's going to happen when you square out your binomials. You're going to get those middle two terms are going to be the same. Last terms. So let's see, running out of colors here. Here we go. Nice. So a negative times a negative is positive. So positive square root of 25, right? The 5's multiply each other because they're under the radical. Let's clean this up. 81. So 81. Let's combine these two. What do I get when I add these two together? Excellent. I'm so happy to hear that you're giving me negative 18 square roots of 5 instead of negative 18 square roots of 10. It's really tempting. People want to add these things together and go, 5 and 5 is going to be 10. No, it doesn't work that way. I wish it did. A lot more people will pass their math exams. That'd be great, but no such luck. Last but not least, square root of 25 is 5. And if you left it like this, you'd leave me in a little bit of a quandary. And basically, you'd be hoping that my favorite sports teams had been winning over the weekend because there's a little bit more that I expect. So what should I write here as my last answer? Thank you. 86 minus 18 times the square root of 5. Yeah, you want to add up the like terms there. All right, you need to. Otherwise, it's kind of like, what do I do? All right, but we can take that decision away from me, make my life easy to just give you 100% on that problem. Let's try a similar one to that. Any questions on this one before I try the next one down? Yes? Going once? Twice? No. Yes. First step. Just multiply the binomial by itself. Let's take a look at this next one. So 12 minus 4 times the square root of 7. And 12 plus 4 square roots of 7. So August, this one's coming directly out of your homework. So hopefully when you do things at home, it'll look a lot like the stuff that we did in class. Same kind of thing that we had with the last one. We'll do the first terms. So first term and then the outside terms. So that would be these two. Then the inside terms, which would be these two. And finally the last terms, which would be these two. And I think I went too far down on that one, but that's all right. We'll work on it. First terms, 12 times 12 is 12 squared. How about the outside terms? What is the 12 going to multiply in that outside term? 12 squared, 144, yeah. 144. I was moving ahead, all right? Good. 12 multiplies the 4, so we're left with 48 times the square root of 7. And it's going to be a positive here. And the middle one, same kind of thing, except we're going to get a negative. Now we got to be careful about the last term. Thank you. Negative 4 times positive 4 is negative 16. Square root of 7 times square root of 7 gives me square root of 49. Those multiplied, right? 7 times 7, they were both underneath the square root, so they multiplied. Something nice happens here, though. Can you see what nice thing is going to happen on this one? These are like terms, but they have opposite sign. 48 and negative 48, that cancels. They're gone. Wow. Isn't that special? That's pretty cool. The 48 comes from the 12 times the 4. And then 12 times negative 4. So the 12 was outside the radical, so it's going to multiply that term, which is outside the radical. in the last one of these, the 7 is under the radical here and here. So you got 7 times 7 gives you the 49. And it's under the radical. So in fact, I can simplify that one a little further. 144 minus 16 times what? 7, which is 144 minus, 112? So 32. Wow, that worked out great. We started out with all these ugly roots, and we ended up with just a nice, friendly number, 32. We're going to need that result later on. Any other comments or thoughts on that one? Yeah, that's it. Like I said, we are going to use this kind of result later. This thing is typically going to happen because when you multiply a minus b times a plus b, well, we've seen this before. You get a squared minus b squared. So those middle terms are going to cancel each other out, and it's just going to be squaring the end terms. And when you square the end terms, you know, all these square roots are going to cancel themselves out. Let's do some more division problems. Let's see. Go back here. These are going to be kind of the same here, where you square it out. So let's try multiple radicals. Let's try some division ones that I'm not seeing right now off of Newton, but these came out of Newton. So let's divide. And let me switch over to here. Divide the cube root of 256 y to the 6th power over the cube root of 2y squared. Okay. The nice thing about division and multiplication is that you can work with radicals the way you would like. And what I'd like to do right now is make that one big radical. So 256 y to the 6th over 2 y squared. Now what's the advantage of that? How did I help myself out by doing that? Yeah, now you can cancel, right? This is going to become the cube root. Well, 2 goes into 256, 128 times. What happens with the y's here? Yeah, subtract the exponents. Well done. So we subtract the exponents. 6 minus 2 gives me y to the 4th. And now, this is a lot more manageable. A number that divides 128 off of our list of perfect cubes. 27 doesn't go in there evenly. Thank you, 64. So 64 here and then a 2 here. How about the variables? What should go there with the variable? Yeah, we want something that's evenly divisible by this index, so that would be a 3 here, leaving you 1 there. Finally, I take the cube root of that. That's going to be 4 and y times the leftovers, which is a cube root of 2y. How are we looking on that one? Not bad? Thumbs up? All right. Excellent. Excellent. Bonus points there. Yay. Let's do one more like that. And this one's actually going to simplify even nicer, I think. This time we're working with square roots. Square root of 12 p squared q to the 5th over 243 p to the 6th q to the 3rd. Now, kind of like the last one, I'm going to start out by rewriting this as one big fraction. 12 p squared q to the 5th over 243 p to the 6th q to the 3rd. Okay, not bad. But what kind of simplification can I do here? Does anyone see a number that divides both of these evenly? There's a couple ways you can get at that. First of all, there's not too many factors of 12, so you start working your way up the list. 2 is not going to work, right? Because this is not even. How can you tell if a number is divisible by 3 evenly without actually doing the division? Does anyone know? Yeah, be a witch. If you add up the digits and get a number that's divisible by 3, then the original number is divisible by 3. So 2 plus 4 plus 3 is 9. Since 9 is divisible by 3, so is 243. Wow, I'm getting a lot of amazed looks. Is that really? You like that one? That's cool. Shut up. So if you add up the digits of a number, like 243, 2 plus 4 plus 3, and get something that's divisible by 3, since 9 is divisible by 3, so is this number. So it works with any number. So for instance, let's take last year's date, right? 2017. So 2 plus 0 plus 1 plus 7. All right, so that's 10. 10's not divisible by 3, so neither is 2017, at least evenly. But what about next year? 2019. Okay, well, that's 2 plus 0 plus 1 plus 9. That's 12. Since 12 is divisible by 3, so is 2019. So let's check it out. 2019 divided by 3 goes in evenly, 673 times. But 2118 or 2017, neither of those is evenly divisible by 3. You get remainders. So it's kind of a cutesy trick. Now, if you don't like that trick, here's a different trick for you. Put in the calculator. 12 divided by 243 gives you this ugly decimal, but then you hit the math key, answer the fraction, and there you go, 4 over 81. So it reduces it for you. So that's the one part of this. So I'm going to have a 4 here and an 81 here. Now for the rest of it, remember what we did in the previous one? We subtracted exponents. So let's work with the q's first. 5 minus 3 gives me q squared. I'm going to do the same thing with the p's, but my suggestion to you is subtract the smaller from the larger. 6 minus 2 gives me 4. P to the 4th, that p to the 4th is going to be in the denominator. So by doing it this way, doing it cleverly, subtract the smaller from the larger, leave it wherever the larger one is, we get down to this. Sure. So both of these numbers are evenly divisible by 3. 12 divided by 3 gives me 4. 243 divided by 3 gives me 81. So that's how we get that first part. With respect to the q's, when you're dividing things with the same base, you subtract their exponents. So 5 minus 2 gives me my q squared there. I'm going to do the same thing here with the p's. It's just that because 6 is bigger than 2, I'll subtract them this way. 6 minus 2 leaves me with 4 of them down in the denominator. That's what I would recommend. I mean, it's really kind of a shortcut, because if you did it, say, the long way would just be longer. It's going to take you a while longer. This is the efficient way. I mean, I could show you, but I changed my mind on that because I'm like, you know what? I'm just going to leave people confused. Let's take the square root of each of these. Now, I'm not going to break it up again. I could. You could break it up as a square root of 4, square root of q squared, square root of 81, and the square root of p to the 4th. I don't expect that. Let's just simplify it. Square root of 4 is 2. What's the square root of q squared? Q. 9. Square root of p to the 4th. That's the only hard part left. P squared. Oh, you're making me look good. Thank you. And that's it. That's a great question. In fact, that was my complaint to Newton today, is that they should write in the instructions, assume the variables are positive. Because without that assumption, then yeah, you certainly want to put the absolute value there. But you don't have to worry about it in this section, as near as I could tell. I did a couple of homework problems, and they weren't working with the absolute value. So yeah, here you don't have to worry about it. On the test, I'll state, assume the variables are positive. And I wrote to Newton. Hopefully they'll fix that. It'd make it a lot cleaner. But bonus points to you, Pat. Yeah, you would want the absolute values there. Yes? It does. So if you want to take a zoom in look at this p squared over p to the 6th, let me do it a couple different ways. One way is to think of it as p times p, and p times p times p times p times p times p, and we can cancel, right? I got one of them here, one of them here, those cancel. It leaves me with 1 over p to the 4th, right? That's an easy way to do it, because you've got 4 of them left. So p times p times p times p is p to the 4th. So 1 over p to the 4th. Another way to do it, like you suggested, if I move this to the denominator, it's p to the 6th times p to the negative 2nd. And when you multiply things with the same base, you add their exponents. So 6 plus negative 2 gives you 4. Now, what I suggested is just subtract the smaller one from the larger one. 6 minus 2 gives you p to the 4. So that's my suggestion. I think that's a friendly way to work on these, but whatever works for you. Do you see how they all fit together? Okay. Yes, good deal. Okay, radical expressions. Let me close that. Let's see. No. All right, let's go to one last little piece from this section, and that'd be this rationalizing. Was it long? Maybe it is. So tell you what, I'll come back to this after a quick break. So about 5 minutes. And we'll start up on this one.
It's hot in this room. I don't know why.
All right, we're still live, just so you know.